All right, so yesterday we focused on finding ordered pairs from polar perspective. So instead of going left and up or horizontal and vertical, we're doing angle measure, and then we're walking out either towards that angle or away from that angle, depending on the radius. Today, what we're doing is being able to convert from polar to rectangular coordinate system, and also from rectangular to polar. But the thing is, you're gonna know how to do this already because of what we did with vectors. So today, it'll feel very familiar, and the steps that we're going to take, you're going to already know. Okay. So polar and rectangular grids do overlap, so that location can take on coordinates from either system. So we can see that full relationship just by looking at a right triangle. Okay. So at the top here, I'm going to have you guys draw a triangle in the first quadrant, a right triangle in the first quadrant. Okay. X and Y would be your rectangular coordinate. And then theta and radius will be used to help you find a polar coordinate. And we know that we can get to one version or x in terms of r and theta by using cosine and sine. So we know that cosine and theta will allow us to connect r and x together. And we know that sine of theta is equal to opposite over hypotenuse. Okay. If I want to solve for x, I can cross multiply. So x times 1 is equal to r cosine theta. Y times 1 is equal to r sine theta. Okay, so we recognize this from vectors, right? Component form, magnitude, cosine theta, magnitude, sine theta, right? And if you know x and y, we can calculate r and theta. Pythagorean theorem will get us to r, just like how we saw in vectors. Since x squared plus y squared equals r squared, if I take the square root, r is just simply square root of x squared plus y squared. And we have a trig function that will connect theta with x and y, and that is tangent, right? We know that since tangent of theta is equal to y over x, inverse tangent, or sorry, yeah, theta will be the inverse tangent of y over x. All right, so we're just now seeing it from polar and rectangular perspective, but we've been using this ever since last unit. Okay, so let's find the rectangular coordinate for each given polar coordinate. So we're going to start with one and convert to the other, and start from the other side, convert. So we're just going to practice converting back and forth between polar and rectangular. Okay. So order pair 4, -60. Let's plot this onto the graph, and then we'll create the rectangular coordinate, and the rectangular coordinate should match with polar coordinate. Okay, it's nice to see how both of them are lining up. Okay, so let's plot this point here. 4, -60. This is in polar form. Okay, so which quadrant are we going to be in here? Fourth quadrant, so -60. And oh, this is not quite showing everything. These are just showing the 30 and 60 degree. The 45 degree is the middle line that we're not seeing. We can draw those in later. But we know -60 is basically 300 degrees. And we're going to walk towards -60 4 units out. So 1, 2, 3, 4. Label that as P. So we have R and theta. We can basically convert into component form from vectors, right? You have your magnitude, you have your theta, you can find your x and y values. Okay. X equals R cosine theta, x equals 4 cosine negative 60. Y equals R sine theta. Okay, let's practice recalling our unit circle values, right? Cosine negative 60. We know cosine is positive in the fourth quadrant, and we know cosine of 60 is 1/2. Sine, we know sine is going to be negative in the fourth quadrant. Sine of 60, we know that's √3/2, so negative √3/2. Sorry, I should put a 4 there here. So my ordered pair, rectangular coordinate, is 2, negative 2√3. And just for graphing purposes, if you plug this in the calculator, negative 2√3 gives you negative 3.46. Now let's plot this point from a rectangular perspective, and we should get to the same point as point P, just a different orientation, right? So if you count 2 units over, 1, 2, and then down 3.464, around 3.5, it lines up pretty close to what we would expect, right? So I just want to convince you that rectangular and polar coordinates, if we convert it correctly, they will both lead you to the same point. Okay, any questions there? Okay, try number 2. Now Q is going to line up more along the 45-degree line. So if you want to kind of draw in that 45-degree line, that should be a diagonal that will kind of go from corner to corner here. So we know 3π/4 is up here. Okay. If we're walking 2 units away from 3π/4, that means you're going to be going into the fourth quadrant, right? So 1, 2. Okay, let's convert this to rectangular form. Okay. Unit circle value, cosine in the second quadrant is negative. We know that anything in the power of 4 family is going to be a √2/2 for cosine. Sine is going to be positive in the second quadrant. Okay, so order pair is root 2, negative root 2. If you want to plot it, calculator, root 2 is around 1.4. Just double check, see if that will lead you to the same point as what we did using polar coordinate. So if I go 1.4 over, and I go down 1.4, yep, looks like it's lining up with consistently with what we would expect from point Q. Okay, any questions so far? Okay, let's look at number 3. Now we're going to go the other direction. We're going to create the polar coordinate, and after we get the polar coordinate, we're going to create additional polar coordinates that refer to the same location. Okay, so this can be a little bit more challenging just because we have to do things in terms of pi and 2 pi, but we'll practice that. Okay, but first, we're going to go through conversion. We know that Pythagorean theorem will get us to our radius. We know that inverse tangent will get us to our theta. Remember, with inverse tangent, we also have to still adjust to the appropriate quadrant, right? So make sure you're in radian mode. Okay, everything turns to radians here. So it's going to feel a little strange because we're used to seeing degrees, right? But we have to leave everything in terms of radians. So in your calculator, go to mode, make sure that you are in radian mode. Inverse tangent, negative 5/2, negative 1.19. Now, 2, negative 5, which quadrant is that in? Fourth quadrant. So we have to add 2 pi, right? Or we got to do 2 pi minus that value. I know degree feels easier because you do 360, but if we're dealing with radians, we have to adjust it, right? 2 pi. .093. Okay, so let's create one order pair. R theta Okay. Or do you get 5.1? Right, you got negative 1.1. Did you get negative 1.19? You didn't? Were you in Radian mode? Oh, no. Yeah, make sure you're in Radian. I know it feels strange because we're used to degree mode, but we have to adjust. Okay. So 5.093, it feels strange, right? Because you're like, where is that degree measure? You just know that it's in the fourth quadrant. Okay. So it feels a little abstract, but I still want us to kind of at least visualize it, right? 5.093 is in the fourth quadrant. It doesn't matter where. Just put a fourth quadrant, and you know that root 29. Okay, some units out. Okay, let's say that's point A. Now, we can create other versions of the ordered pair by doing what with 5.093 to get another what's a way to get a coterminal angle? Good. Add or subtract 2 pi, right? I know we're used to 360 because it just feels more natural, but with radians, we got to just think abstractly here. I got to add or subtract 2 pi. I can't really add 2 pi. If I add 2 pi, I'm already going to be outside this interval, so I'm going to subtract 2 pi. To get it. And negative 2 pi and 2 pi, that's around negative 6.2 and 6.2. So you know that just to kind of give you some frame of reference, decimal-wise, 2 pi is 6.3 or 6.28. So ultimately, we want our theta value to be between negative 6.28 and 6.28. Okay, so if I subtract 2 pi, we should still be in that interval, right? So 5.093 minus 2 pi, we're still in the fourth quadrant, so we can still keep our radius positive. Okay, minus 2 pi, negative 1.19. Okay, so we can create order pairs from the fourth quadrant's perspective, but we can also create order pairs from which other perspective? Second quadrant, right? So we can also find the second quadrant and then walk out away from the second quadrant and do negative radius, right? So how can I get to the second quadrant if I am sitting at the first quadrant, 5.093? What's a way for me to move to the other quadrant? Add or subtract what? Yep. And what's a way for us to say 180 in terms of radians? Pi. Okay. Good. So with 5.093, we can add pi. I'm sorry, subtract pi. We're going to subtract pi because otherwise I think we'll be outside the interval. So, okay, so we're in the fourth quadrant. We want to live in the second quadrant perspective. So subtract pi. So 5.093. I know this feels harder because you prefer to just have degrees, right? If it's like 300 degrees, you subtract 180, and it just feels more natural. But now we're dealing with these decimals, it just feels a little bit more strange, but just have to kind of keep in mind what you're doing here. So 1.951.
It's negative.
And it's negative, right? If 1.951 is in the second quadrant, we have to walk away from the second quadrant in order to get to that fourth quadrant. So we have to do negative root 29. And if I'm at second quadrant, 1.951, what's another way to represent this coterminal angle here? Add what? Add 2 pi, right? If I add 2 pi from second quadrant, I'll be still in the second quadrant and still be within that negative 6.28 and 6.28. So second quadrant, I can add 360, or in our case, add 2 pi to get to still be in the second quadrant. Oh, it's a little too big. So I need to do 1.951 minus 2 pi. Negative 4.33, all right. Okay, so I think the hard part is understanding where you are and either adding or subtracting 2 pi to get to the same location, but you can also add or subtract pi to get to the opposite, the diagonal quadrant, and then be able to walk backwards to still achieve the same location. Okay, any questions there? Okay, so try number 4. Number 4 should feel very similar process, and see if you're able to work through that. So we know that we're in the third quadrant. I can go the diagonal quadrant, which is first quadrant. I can subtract pi, and that will take me to the first quadrant. And I can just change the radius to the opposite sign to walk away from the first quadrant and still land in the same point. And then if I'm in the first quadrant already, I can create another coterminal angle that's in the first quadrant. All right, I can subtract 2 pi. And that will give me another variation of the first quadrant. And I can walk away from the first quadrant as well to get to the third quadrant. Yes.
So will it be the same kind of like formula thing going on where it's subtracting minus 2 for every like order pair?
Yes, yeah. If you're in polar coordinate, you can always do this add and subtract 2 pi or add or subtract pi to either get to the same location or go to the opposite location.
Okay.
Yeah. Mm-hmm. I know this feels more difficult just because it's harder to locate those radian measures in your heads because we're used to degree measures, but yeah, just have to kind of understand that process and just be used to these numbers as well. Okay, any questions? So it's not hard, it just takes a little bit of time to kind of get used to understanding where we are in a more abstract way. Okay, there's one more topic, and that is distance formula. We have distance formula for polar coordinates. It's going to look a little messy, but if we're just careful and just enter everything into the formula, then the calculator will do all the work for us. Okay, page 6. Does anybody still need this page? Okay, page 6. Okay, so how do we find distance between 2 points? We're not going to do a full problem, but I just want to kind of show you that this is a distance formula we've been using in the past, right? You take 2 points, you subtract the x's, square it, you subtract the y's, you square it. It's almost like component form in Pythagorean theorem, right? That's how you find the distance between 2 points on a Cartesian or rectangular plane. But for polar plane, we have a slightly different formula, but you can kind of see the relationship. We're not going to prove it, but we're just going to kind of learn how to use it. So here's the polar distance formula. Okay, assuming that you have point 1, R1, theta 1, and then you have point 2, which we can call R2, theta 2. So here's the formula. It's still a little bit of Pythagorean theorem going on, but we have to adjust for this change in slightly different format here. So we'll add the radius after we square them, minus 2r1 r2 cosine of theta 2 minus theta 1. Okay. Feels kind of messy, but if we're careful and just enter everything in piece by piece, we can make the calculator do all the work for us. Okay, so here's the example we're going to practice here. Find the distance between points A and B. I'm going to call them points A and B. Let's plot them just to see what we're trying to accomplish here. So -3 pi over 3, that means first quadrant. We're going to walk away from the first quadrant into the third quadrant. So pi over 3 is the one that's closer to the y-axis. We'll go 1, 2, 3.8. Okay, and I'll label this R1 theta 1. Point B, -11 pi over 6. All right, that means if I add 2 pi to this, that's really pi over 6. So it's all the way over here, pi over 6. We're going to walk 5 units towards pi over 6. So ultimately, we're trying to find that distance, that straight line distance between points A and B. Okay, so we're going to enter everything in as we see it. We'll do it piece by piece. Okay, R1 squared. R2 squared. I'm not even putting a negative here because I know that's just going to turn to be a positive. Two R1 R2. That's 2 times negative 3 times 5. And a cosine of theta 2 minus theta 1. So theta 2 minus theta 1. Okay. You can try to enter all this into the calculator, but I like to kind of break them, kind of do it piece by piece here. And then I just entered in cosine of negative 11 pi over 6 minus pi over 3. Make sure you're in radian mode. I got root 3 over 2. And then I just entered all this in the calculator. Now you can try doing it all at once. For me, I just like to kind of break things apart before I do it all into the calculator. But we should be satisfied with the decimal approximation to 3 decimal places. Okay, trying the next example. What's different about this next example here? Degree. So yeah, make sure you go to the calculator and go to degree mode. Otherwise, your number will come out a little different. Check your answers, see if you got the same thing as me. changes to the screen. Mm-hmm. Okay, let's go to page 7. Do some classwork problems here. Does anybody still need this page? Okay, so here's the classwork that we're going to be doing here. 1 3 5. So you're just going to convert from polar to rectangular. And then 13, 15, 17, 23. These are the ones that feel more like the previous pages where we have to get to polar coordinates in radians and then create 3 other additional points. Okay, so I'll work this out the same time that you guys are doing them, and then check our answers, and then I'll walk around and check you guys off. Okay. So 1 3 5 for the top portion, and the bottom portion 13, 15, 17, 23. Okay, great, thank you. Guys, 13 through 23, make sure you're going back to Radian mode. Okay, Radian mode. bottom half. Guys, for the bottom half, just do 13 and 15. Okay, just 13 and 15. If you can get through two of them, you have a good idea as to how to do them. So okay. Just 13 and 15, create 4 order pairs for each of them. Is anybody still working on 1, 3, and 5? Oops, sorry. I need to subtract 2 pi here. Okay, let me check your 3 pages, pages 5, 6, and 7.